Hello. So today we're going to be talking about is this really exciting theorem, and it's called the first fundamental theorem of calculus. And it's really exciting because now we don't have to do sums and the limit as n goes to infinity to find the area under a curve or to evaluate a definite integral. We can just use this instead, and it's much easier, much faster. So what the first fundamental theorem of calculus says is that if f of x is continuous on a to b, and big F of x is an antiderivative of little f of x, then to evaluate the definite integral from a to b of little f of x, we're just going to take the antiderivative of b and subtract the antiderivative of a. And so now you might be thinking, well, where did the constant integration go? Because normally when we were doing the indefinite integrals before, we got big F of x plus c. But now if we add on these constants of integration, and we draw what this is called an evaluation symbol. So this would read big F of x plus c evaluated from a to b. And we plug in correctly. So we do antiderivative of b plus c minus the antiderivative of a plus c, and then distribute our negative sign. We're just going to get antiderivative of b plus c minus the antiderivative of a minus c. Our c's cancel and we get exactly f of b minus f of a. And you always want to make sure you're plugging them in the correct order. You always do the top first minus the bottom. So always remember top minus bottom. And if you do bottom minus top, you get the same number, but you get the negative of the correct answer. So you just want to be careful with what your signs are. So let's do an example. Let's evaluate from -2 to 3 of x squared minus x minus 2. So first we're going to evaluate the indefinite integral. So to do that we need our power rule. So the antiderivative of x squared is going to be x. Using our power rule, we're going to add 1 to 2, divide by the new exponent, minus x, add 1 to the current exponent, divide by the new one, minus 2. And since there's no x there, doing the antiderivative just gives us an x. And then we're going to draw our evaluation sign, which reads evaluated from -2 to +3, which is just going to be x cubed over 3 minus x squared over 2 minus 2x evaluated from -2 to +3. And so now we're just going to plug in, and we're going to be really careful to plug in the correct order. So we have to do the 3 first. So we're going to get 3 cubed over 3 minus 3 squared over 2 minus 2 times 3 minus, plugging in -2, we're going to get -2 cubed over 3 minus -2 squared over 2 minus 2 times -2. And these sets of parentheses that I'm putting around each thing, each antiderivative being evaluated at -2 and 3, they're really important because we have to know to distribute the negative sign in between. So 3 cubed over 3 is really just 3 squared, so we're going to get 9 minus 9 halves minus 6 minus -2 cubed is -8, so we're going to get -8 cubed minus 4 over 2, so we're going to get -2 plus 4. So now if we just simplify inside and then distribute our negative sign, we can get an answer. So 9 minus 9 halves. Whoops, we can actually do 9 minus 6. So let's make that a 3 minus 9 halves minus a -8 thirds plus 2. Now we're just going to distribute our negative signs. So we're going to get 3 minus 9 halves plus 8 thirds minus 2. So we're going to get 1 minus 9 halves plus 8 thirds. So if we put everything into a common denominator, which our common denominator here is going to be 6, we're going to get 6 over 6 minus 27 over 6 plus 16 over 6. So 6 minus 27 is going to give us a -21 plus 16 is going to give us a -5/6 as our final answer. So that's how you go about using the fundamental theorem of calculus, the first fundamental theorem rather, to evaluate a definite integral. So now let's use that fundamental theorem to evaluate the total area between -2 and 3 of the same function. So what we talked about in the last video is how to correctly analyze the area under the curve, the total area. So what we want to do is we want to split this up into three separate intervals of area. So this is the area that we're trying to find. What we're going to do now is we're going to label this one as A1, A2, and A3. So to find the total area, we want to split this up and do three separate integrals, and then add and subtract them properly to counteract any negative signs that we might have. Because A2, since it's below the x-axis, is going to be negative. So our total area is going to be equal to A1 minus A2 plus A3. So we want to find what each of these are individually. So these red dots here are at -1 and +2. So first we're going to find A1. So A1 is going to be equal to the integral from -2 to -1 of x squared minus x minus 2 dx. And since we already just did the same integral in the previous example, we know that its antiderivative is x cubed over 3 minus x squared over 2 minus 2x. So now all we have to do is evaluate from -2 to +1. So we always start with the top, so we're going to plug -1 in first. So we're going to get -1 cubed is -1/3 minus 1/2 plus 2 minus, now plugging in -2, -2 cubed is -8/3 minus, we're going to get +4/2, so we're going to get -2 plus 4. So now we're going to get -1/3 minus 1/2 plus 2 plus 8/3. And I can rewrite -2 plus 4 to just be a plus 2. So I'm really going to get a -2 here when I distribute the negative sign to it. My plus 2 and my -2 are going to cancel. And we're going to get 7/3 minus 1/2, which is just going to be 14/6 minus 3/6, which is equal to 11/6. So that's A1. So we might even label that over here as 11/6. So now we're going to do the same process to find A2 and A3. So for A2, that's just the integral from -1 to +2 of our function y. So instead of writing it all out, I'm just going to write y there since we know it's the same function. So now we're going to do x cubed over 3 minus x squared over 2 minus 2x. Evaluate from -1 to +2. So we plug in the +2 first. So we're going to get +2 cubed is 8, so 8/3 minus 2 minus 4. Plugging in the 2. So then we're going to get minus, we plug in -1, we already know that we're going to get -1 cubed minus 1/2 plus 2 from the previous problem, which means we're going to get 8/3 minus 6 plus 1/3 plus 1/2 minus 2. We simplify, we're going to get 9/3, which is 3 minus 8 plus 1/2. So we're going to get -5 plus 1/2, which is just -10/2 plus 1/2. So we're going to get -9/2, which we knew it was going to be negative because A2 was all under the x-axis, so we knew that it was going to be a negative area. So now all we have to do is find A3. And that's just going to be the integral from 2 to 3. If we look back on your graph, you can see that it starts here at 2, ends here at 3. So that's where we get the limits of integration from. So we're going to get 2 to 3 of our function y dx, which means that we're just going to evaluate the same antiderivative of x cubed over 3 minus x squared over 2 minus 2x, now from 2 to 3. So 3 is on top, so we got to plug that one in first. So 3 cubed is 27 divided by 3, so we're going to get 9 minus 9/2 minus 6 minus, and we know when we plugged in 2 from before, we got +8/3 minus 2 minus 4, or minus 6. So now if we simplify, we get 3 minus 9 halves minus 8 thirds plus 6. So 3 plus 6 is 9, minus 9 halves minus 8 thirds. Our common denominator here is again going to be 6, so we're going to get 54 over 6 minus 27 over 6 minus 16 over 6, which is just going to be equal to, doing the arithmetic, 54 minus 27 is 27. 27 minus 16 is going to give us 11, so we're going to get positive 11 over 6. So our total area now is going to be equal to the area of A1, which we found to be 11 over 6, minus negative 9 halves to counteract the negative area of A2, and then plus A3, which was 11 over 6 again. So now we're going to get 22 over 6 plus 9 halves, which is equal to 22 over 6 plus 27 over 6, multiplying the second fraction by 3 over 3, which is just going to be equal to 49 over 6. So the total area of that function bounded between the function and the x-axis between negative 2 and 3 is going to be 49 over 6. Okay, so one more thing to talk about then, and we're just going to do another example problem, and we're going to do the definite integral of an absolute value function, which we already have graphed for you on the screen. So we're going to do between 0 and positive 2. So we're going to go 0 to positive 2. Now the thing about absolute value is that you technically don't have a derivative at the cusp. So there's no derivative here. So because it's not differentiable there, we want to split the integral up into two separate integrals. So this line of the absolute value is really just the line negative 2x plus 1. And this line here is just opposite. It's 2x minus 1, which you can find easily by taking 2 points, like a point here and a point here, and counting off the slopes. You go up 2 and left 1, which gives us the slope of negative 2. Y-intercept is obviously at 1. And then same thing here. You have a point here and a point here. So you go up 2, right 1, they give us the positive slope of 2. And if you continue this line down, it would go through a y-intercept of negative 1. So to evaluate this integral, what we're going to do is we're going to use that additive property of integrals, and we're going to split it up from 0 to 1/2 of the line negative 2x plus 1 dx, plus the integral from 1/2 to 2 of 2x minus 1 dx. And we're doing that because there is no derivative at 1/2 at that cusp point. So we have to split it up into two integrals because the derivative on the left-hand side of the cusp point is different than the derivative on the right-hand side. So the integrals will be different as well. So now we're going to do the antiderivative of negative 2x is just negative x squared plus x, evaluated from 0 to 1/2, plus x squared minus x, evaluated from 1/2 to 2. Which we just found using the power rule. So if you need a review of that, just go back to the 4.1 videos and watch the integration, the indefinite integral videos about that. So now we're going to plug in the 1/2 first. So we're going to get negative 1/2 squared plus 1/2. Put brackets around the first one as well. Minus 0 squared is 0 plus 0. So we don't even really need that one. And then plugging into the second one, we plug in the 2 first because it's on top. So we get 2 squared minus 2 minus 1/2 squared minus 1/2. And now we're just going to simplify. Okay, so 1/2 squared is 1/4, so we're going to get negative 1/4 plus 1/2. This here is all 0, so we don't even need to write that. So then we're going to do plus. This is going to be 4 minus 2 in here, so we're going to get 2. Minus, this is 1/4 minus 1/2, so we're going to get minus 1/4. Distributing that negative sign, we're going to get plus 1/2. So combining all of our like terms, we're going to get negative 2/4 plus 2 plus 1 when we add those two halves together. So we get negative 1/2 plus 3, which is just negative 1/2 plus 6/2, which is positive 5/2. So that's how you evaluate a definite integral of an absolute value function. You want to split it into two integrals and take the integral of the left-hand part of the absolute value and then the integral of the right-hand part. So you split it at that cusp point. Okay, so thank you so much for watching. Have a great rest of your day.